Welcome back to this next video in which we are discussing the cardiac cycle and cardiac electrophysiology. Okay, so we've now discussed the propagation of this electrical signal through the cardiac tissue and how it's actually going to lead to the correct portions of the myocardium contracting at the correct stages. What we now want to talk about is what is the actual nature of this electrical signal, and in particular how is it generated. So we're going to start off then with a sinoatrial node cardiomyocyte, and we want to discuss how does this sinoatrial node cardiomyocyte generate an electrical signal every 0.8 seconds. Okay, so this we will suppose this rectangle is representing our sinoatrial node cardiomyocyte. Now, of course, before we can actually talk about how the sinoatrial node cardiomyocyte actually generates the electrical signal every 0.8 seconds, we need to talk about what is the actual nature of this electrical signal. What is it? Okay, how are we actually encoding some sort of information? What is the actual nature of it? Okay, so the one-line answer to what is the nature of the electrical signal is that it is a change in the electrical potential difference across the cell membrane. Okay, and to understand what that actually means, we need to know what is meant by the electrical potential difference across the cell membrane. And in order to understand that, we need to know what is meant by electrical potential. So what I'm going to do is actually go down right to the foundations, start by telling you what is meant by electrical potential, and then we'll work up to understand what the actual nature of this electrical signal that will propagate it from cardiomyocyte to cardiomyocyte is actually going to be. Okay, so let's start off then with discussing what is electrical potential. So electrical potential is this concept from physics. It is a mathematical model to help us understand this reality that we live in. And this is the mathematical model. What you do is you ascribe to every point in three-dimensional space a real number, and this number is going to be called the electrical potential. So to draw a picture of this, let's draw a three-dimensional grid like so. So these are the three perpendicular axes, one in the plane of the piece of paper, this one's also in the plane of the piece of paper, and then we're imagining that this one is perpendicular, so like that. Okay, and then to every point in three-dimensional space you are going to ascribe a real number. So it can be positive, it can be negative, it can be zero, it can be rational, it can be irrational, it can be transcendental. You are not allowed, however, to go into the bigger number system that is the complex numbers. Okay, so you must stay in the real numbers. So you're going to give every point in three-dimensional space a real number, and that real number will be called the electrical potential, and we'll denote it capital E. So every point then has this number ascribed to it. Now, because we're working in physics, of course, quantities need to have units. So what's the units for electrical potential? Well, the units for electrical potential are the volt. Okay, so you will measure the electrical potential at any point in volts. Okay, so this means that in principle what I could have is a little man here with a device, so this is a machine, for measuring electrical potential, and what he could do is he could go around this three-dimensional space and actually ask for each point what is the electrical potential at that point, and he'd get this number coming up on his screen. Okay, so that's the basic concept of electrical potential. Now, of course, that's brilliant, but what does this actually mean? Well, firstly, what you want to know is what actually determines the electrical potential at a point. Well, what determines the electrical potential at each point in three-dimensional space is the distribution of charge. So there are charged particles in the universe, positively charged particles and negatively charged particles. Okay, they are spread out all over the universe. So for instance, protons are positively charged particles, electrons are negatively charged particles, the main constituents of atoms there. Okay, they're spread out all over the universe, and positively charged particles will raise the electrical potential at the nearby areas to them, and negatively charged particles will lower the electrical potential at the points near to them. So it is the distribution of charge in the universe that tells which determines what the electrical potential at every point in the universe is. Okay, and of course there are exact formulas that tell you how to work out the electrical potential at each point given the distribution of charge. However, of course, we're not going to go there. Okay, so in principle, from the distribution of charge in the universe, you can work out what the electrical potential at every single point is. In turn, and this is where it's really quite beautiful, this model, in turn, the electrical potential distribution in the universe tells charged particles how to move. So the distribution of charged particles tells each point of the universe what electrical potential to have, and the distribution of electrical potentials to the points in space tell the charged particles how to move. So if there is a difference between the electrical potential at one point and the electrical potential at another point, so let's say we've got point 2 over here, and let's say the electrical potential at point 2 is different from the electrical potential at point 1, okay, we would say there is an electrical potential difference between the two. That has the tendency to make charged particles move, and which direction they move in will be determined by whether they are positively or negatively charged particles. So positively charged particles want to move to areas of lower electrical potential, and negatively charged particles want to move in the opposite direction to areas of higher electrical potential. And overall, what ends up happening is charged particles, they will end up moving around to try and destroy electrical potential differences, okay? Because that's the only way that an equilibrium can ever arise. If the electrical potential is even everywhere, then charged particles would stop moving. So that's a very important concept, because now let's go back to our cell. All of the points inside the cell here are going to have the same electrical potential because they're all in electrical equilibrium with one another. Charged particles can move between different points inside the cell, and as I say, they will move in a way that makes the electrical potential distribution in space even, basically, okay, because as I say, that's the only way there will ever be an equilibrium, the only way they'll ever stop moving. If you have uneven electrical potentials, then that will cause movement of charged particles. The only way movement will ever stop is if the electrical potential is even everywhere. So charged particles will move to try and rebalance and even out the electrical potential everywhere. So because all of the points inside the cell are connected with one another and charged particles can easily move between them, it ends up being the case that all the points inside the cell are going to have the same electrical potential. So we will denote that by capital E for electrical potential and then subscripted I for intracellular. So this is denoting the electrical potential at all points inside the cell. So if I had my little man here and he was to walk around any point inside the cell and ask what is the electrical potential at all these points inside the cell, he would get the same number on his screen, which is the electrical potential intracellular here. Okay, then it's the same story for extracellular. For the extracellular fluid, all the points in the extracellular fluid are in electrical equilibrium with one another, so their electrical potential will all be the same. So if the little man was to walk around anywhere in the extracellular fluid and ask what is the electrical potential there, he'd get the same answer everywhere, and we'll call that capital E for electrical potential, subscripted capital E for extracellular. Okay, now, the electrical potential extracellularly and the electrical potential intracellularly, however, do not need to be the same, because the intracellular and extracellular compartments are not in electrical equilibrium, because look, there is this cell membrane in the way. Okay, this stops charged particles from being able to move between the two compartments. So that results in the two compartments not being in electrical equilibrium, and indeed usually these two values are not the same. So there is an electrical potential difference between the extracellular compartment and the intracellular compartment. Now there is another word that people often use for electrical potential difference, which is voltage. Okay, so we're now introducing this very important concept of electrical potential difference. So this just means a difference in the electrical potential between 2 points, or a voltage between 2 points. So there is a voltage across the cell membrane and an electrical potential difference across the cell membrane. They mean exactly the same thing. Okay, right, so usually the voltage across the cell membrane is denoted capital V and then subscript M for the voltage across the membrane. And what this means is the electrical potential difference from extracellular to intracellular. And this is important. You can't just say the difference between 2 points. You have to give it a direction. It has to be from one point to another. And if you were to set the arrow in the opposite direction, all it would do is flip the sign of the electrical potential difference. But you do need to give a direction. And when we talk about the electrical potential difference across the cell membrane, when physiologists talk about that, they mean always from extracellular to intracellular, because the physiologist always starts outside the cell and then will put some probe into the inside of the cell. Okay, so this means if the little man was to start off extracellularly and he measured the electrical potential extracellularly, got some number up on his screen, and then he moved into the intracellular compartment, got a new number on his screen, how much would the number have changed? What would he have to add on to this number to turn it into this number? Okay, and of course this is just going to be the electrical potential after the jump, so after he's arrived here, subtract the initial electrical potential, which is the electrical potential extracellularly. And of course you can hopefully see that if you were to add this to the electrical potential extracellularly, you would just get the electrical potential intracellularly. Okay, so this is the formula then for the electrical potential difference across a cell membrane. And across a sinoatrial node cell, and indeed across loads of cells in the body, because most cells in the body have an electrical potential difference across their cell membrane. I think it's actually all cells in the body. Okay, across most cells in the cell body, the electrical potential difference is negative 65 millivolts. And indeed for the sinoatrial node cells, it's going to be that, or around there. Okay, so what does this mean? This means if you were to jump from the extracellular compartment into the intracellular compartment, your electrical potential will go down. That's why it's negative here, and it will go down by 65 millivolts. Now note, electrical potential difference, the units for that are going to be exactly the same as the units for electrical potential, because it's just one electrical potential subtract another electrical potential, so the units aren't going to change. Millivolts just means 1,000th of a volt, so you could equally well have written this as negative 0.065 volts if you like. Okay, so it's a small difference in the electrical potential between the extracellular compartment and the intracellular compartment. So the extracellular compartment has a higher electrical potential than the intracellular compartment. Okay, the intracellular compartment's electrical potential is more negative than the extracellular compartment's electrical potential. So usually, cells just keep the same electrical potential difference across the cell membrane, and they sit there just keeping the same electrical potential difference across the cell membrane. Not in the case of the sinoatrial node cells. What they are going to do is that all the time, every 0.8 seconds, they are going to generate a disturbance in the electrical potential across the cell membrane. They're going to change this value. In fact, they're going to make it less negative, and they're actually going to turn it positive, so that the intracellular compartment actually ends up with an electrical potential higher than the extracellular compartment. And it is this change in electrical potential difference across the cell membrane that constitutes the electrical signal. Okay, and this applies not only in sinoatrial node cells, but it's going to be the same change that's going to occur in all of the cardiomyocytes in the heart. And indeed, this is the same form that the electrical signal across nerve cell membranes takes. It's the same electrical signal all over the body. When we talk about electrical signals, the nature of it is that it's just a disturbance in the electrical potential difference across the cell membrane. Okay, so now that I've explained what the actual nature of the electrical signal that's going to be generated across the cardiomyocyte membrane actually is, let's talk about how sinoatrial node cells are actually going to generate a disturbance in their electrical potential difference across the cell membrane every 0.8 seconds. Okay, so often when we talk about things like this, and by the way, now will probably be a good time to introduce a key word, key phrase, action potential. The action potential is the name that we give for this transient change in the electrical potential difference across the cell membrane. So the electrical signal we've discussed is going to be this change in the electrical potential difference across the cell membrane, and the name for that is it's called an action potential. So electrical signals across cell membranes are of this form, an action potential. And whenever we talk about action potentials, from now on, rather than talking about electrical signals, I'm going to talk about action potentials. It's just a new expression that we use to mean the same thing. Whenever we talk about action potentials, often we draw graphs of the electrical potential difference across the cell membrane, the voltage across the cell membrane versus time. Okay, so the x-axis here is going to be time, and on the y-axis we're going to have the electrical potential difference across the cell membrane. So it starts off down here at negative 65 millivolts here. So this dot here is meant to be representing negative 65 millivolts. So up here is the positive electrical potential difference, down here is obviously negative. Okay, so what's going to happen then to cause this change in the electrical potential difference across these sinoatrial node cell membranes? Well, sinoatrial node cells have a very special channel. Okay, and actually, before I jump into that, let me tell you more foundationally, how do we actually produce a change in the electrical potential difference across the cell membrane? Well, what we're going to have to do is we're going to have to alter the electrical potential intracellularly and the electrical potential extracellularly. How do we do that? We move charged particles across the cell membrane. Okay? So all of this is going to be about allowing charged particles to move across the cell membrane. And in order to understand this, what we should mention is the fact that there are gradients of ions across the cell membrane. Okay, so I'll just go back to talking about this before we actually go on to discuss the generation of the action potential. So not only is there a gradient in the electrical potential across the cell membrane, there is also gradients in ionic concentrations across cell membranes. So importantly, for sodium ions, potassium ions, and calcium ions, there are gradients across the cell membrane, and I'm just going to give you the numbers here. So sodium ions are in a much higher concentration in the extracellular fluid than in the intracellular fluid, and these numbers will vary depending on your source, but usually people quote the extracellular sodium concentration as being around 145 millimolar extracellularly and around 12 millimolar intracellularly. Okay, so there is around a 12-fold concentration gradient of sodium favouring its movement into the cell. So if you were to open channels across the cell membrane, this would be favouring the movement of sodium into the cell, and that's an important concept to bear in mind. It's going to become really important. Okay, for potassium, it's the opposite way around. Potassium is much higher concentration inside the cell. It's got an intracellular concentration of around 155 millimolar and an extracellular concentration of around 4 millimolar. So that's about a 40-fold gradient favouring the movement of potassium out of the cell. For calcium, it's an extremely powerful gradient. It dominates these two. It makes them very weak gradients in comparison. So the extracellular calcium concentration is around 1.5 millimolar, okay, which looks low compared to the sodium and potassium concentrations we've been talking about, but then the intracellular calcium concentration is 100 nanomolar. Okay, that's a 15,000-fold gradient of calcium across the cell membrane, favouring its movement into the cell. Okay, and those are the important ionic gradients that we need to know about. So across the cell membrane you have these gradients in concentration of the ions. Okay, right, so now we are actually ready to start talking about the generation of an action potential in sinoatrial node cells. So let's say, once again, here is our sinoatrial node cell, and that's a little bit small, but never mind, I'll try and fit it in here. So, the incredible thing that sinoatrial node cells have, which causes the pacemaker activity, which causes them to generate electrical potential differences across their, changes in the electrical potential difference across their cell membrane automatically, okay, every 0.8 seconds, is they have a channel that opens when the electrical potential difference across the cell membrane is quite negative, okay, for instance, at around negative 65 millivolts. Okay, so I'll draw this here. So here is this ion channel in the cell membrane, and I should stress that normally the ions cannot move freely across the cell membrane, so they have to go through channels to get across the cell membrane. Okay, so there's going to be a very special channel then in the sinoatrial node cell membrane, which is known as the HCN channel, standing for hyperpolarization. That's what the H is here for, hyperpolarization. polarization. So this is just reflecting the fact that when the cell membrane is hyperpolarized, which means that the electrical potential difference across the cell membrane is quite negative, okay, the channel is going to open. Okay, so hyperpolarization just means the electrical potential difference across the cell membrane is quite negative. Depolarization means the electrical potential difference across the cell membrane is quite positive. Okay, so hyperpolarization is the H, and then the C is for and cyclic nucleotide gated. So the N is then for nucleotide. So and cyclic nucleotide gated, and then it's just ion channel. Okay, so ion channel. So cyclic nucleotides, in particular cyclic AMP, has an influence on this channel, and in fact that is very important in the mechanism by which adrenaline and noradrenaline can increase the rate at which the heart is beating, can increase the rate at which the sinoatrial node cells generate action potentials, but we're not going to talk about that here. We're just going to talk about basics. Okay, so here is this HCN channel, and the key thing to understand is that this channel is usually closed, and it is a channel that allows sodium ions to move across the cell membrane. Okay, but when the electrical potential difference across the cell membrane goes into hyperpolarized regions, such as negative 65 millivolts, this channel is going to open. Now that is extremely rare. Most channels that open because of changes in the electrical potential difference across the cell membrane open when the electrical potential difference depolarizes. There are very few that open when it hyperpolarizes. This is the channel, fundamentally, that is responsible for the sinoatrial node cells generating an action potential automatically. Okay, so at negative 65 millivolts, what's going to happen is all of the HCN channels that the sinoatrial node cell has, and of course I'm drawing one here, but they'll be all over the cell membrane, they're all going to start opening. And as I say, they will conduct sodium ions. Now let's think about this. We know that the extracellular concentration of sodium is 145 millimolar, whilst the intracellular concentration is around 12 millimolar. So the concentration gradient is favouring the movement of sodium in. So it's saying you're going to get a net movement of sodium in when you open this channel. In addition, think about the electrical potential difference across the cell membrane. It's negative 65 millivolts. That means the intracellular electrical potential is lower than the extracellular electrical potential. Sodium ions are positively charged ions. They want to go where the electrical potential is lower, which is the intracellular compartment. So both forces are favouring the movement of sodium ions in. So indeed, when you open these HCN channels, you are going to get a net movement of sodium ions into the cell. Okay, now sodium ions are positively charged ions. Where they go, they raise the electrical potential. So now what's going to happen to the intracellular electrical potential? We're bringing sodium ions into the sinoatrial node cell. That means the electrical potential intracellular is going to go up. What's going to happen meanwhile to the extracellular electrical potential? We are taking positive charge away from the extracellular compartment, so that means the electrical potential extracellularly is going to go down. So what's that going to do to the electrical potential difference across the cell membrane? Well, here's a good way of visualizing it. Previously, it was like this. Okay, we can draw a simple diagram like this. Here, let's say this represents the electrical potential extracellularly, and when we went inside, we had to step down in electrical potential. We had to go down by 65 millivolts. But we have now lowered the electrical potential extracellularly, and we've raised the electrical potential intracellularly. So how much are we going to have to step down now? Less. So in fact what this is going to do is it's going to make the electrical potential difference across the cell membrane less negative. It's going to depolarize the cell. So that's an extremely important key word. Depolarization refers to the making less positive the electrical potential difference across the cell membrane. Okay, so what this first portion then is going to look like is it's going to look like this. We're going to have a line like this where the electrical potential difference across the cell membrane is depolarizing. It's becoming less negative. Okay, now what will then happen is when this passes a certain point, and this is exactly like what would happen in neurons, once it passes a certain point called the threshold potential, which is usually around negative 40 millivolts, it will then fire a preordained action potential. Okay, it will generate one of these these changes in the electrical potential difference across the cell membrane, just as can be generated in normal cells. So normally, in order to, well, actually, let me just go back a bit. So these electrical signals across the cell membrane, they take a certain form always, okay? You can't just vary the electrical potential difference across your cell membrane in a haphazard way as you please. What happens is once you get up to a certain point, once you depolarize the electrical potential difference up to a certain point called the threshold potential, what then happens is a set series of events to trigger an exact signal, an exact type of alteration in the electrical potential difference across the cell membrane. And no matter what it was that triggered the depolarization up to the negative 40 millivolts, the threshold electrical potential difference here, the signal after that, i.e. how the electrical potential difference across the cell membrane will vary, will be exactly the same. So now that we've got up to negative 40 millivolts, everything's set here. Okay, this channel has done its job, and in fact very soon it will start to close, because remember, it's activated by hyperpolarization. So the more you depolarize the cell membrane, the more likely it is that this thing is going to close, because it likes to be open at very negative electrical potential differences across the cell membrane. So this is the thing that fundamentally triggers the pacemaker activity. This is what triggers the generation of an electrical signal every 0.8 seconds. Now that we have got depolarization up to negative 40 millivolts, it's going to be just like it would be in neurons. Okay, so if you are aware of how action potentials occur in neurons, you'll know what I mean. If you're not, if this is your first exposure to action potentials, what's going to happen is a set series of events that is very similar to what would happen in neurons. Okay, so what's now going to happen is voltage-gated channels are going to open, and these are more normal because these are channels that are opened by depolarization of the electrical potential difference across the cell membrane. Now in neurons it would be voltage-gated sodium channels that would now open, and indeed in the rest of the cardiomyocytes, apart from the sinoatrial node cells and the atrioventricular node cells, it's going to be voltage-gated sodium channels. However, in sinoatrial node cells, and as we'll see later, AV node cells as well, it is actually T-type voltage-gated calcium channels that are going to open instead of voltage-gated sodium channels. Okay, so these are very similar to voltage-gated sodium channels, except that they are permeable to calcium ions rather than sodium ions, but their properties in terms of how quickly they open and how quickly they close are very similar to voltage-gated sodium channels. So what's now going to happen, once the electrical potential difference across the cell membrane of this sinoatrial node cell has got to negative 40 millivolts, is that T-type voltage-gated calcium channels are going to open all over the cell membrane, and they're now going to allow calcium ions into the cell. Now you don't even need to think about this. The calcium ions are going to move into the cell, because remember there's that 15,000-fold gradient favouring the movement of calcium in. You can also argue, because the electrical potential difference across the cell membrane is still negative, that will be favouring the movement of calcium into the cell as well. Okay, and when you bring in calcium ions, you're again bringing in positive charge into the cytoplasm of the sinoatrial node cell. That will raise the electrical potential intracellularly. It'll decrease the electrical potential extracellularly, because you're taking the positive charge from the extracellular fluid. So what's going to happen is you're actually going to get an extremely rapid upstroke, an extremely rapid depolarization, and it will actually cross the axis here. Okay, the electrical potential difference across the cell membrane will actually become positive. The electrical potential intracellularly will start to become higher than the electrical potential extracellularly. And you might say, well, surely now the calcium will start going out, okay, because it doesn't want to be in the intracellular compartment anymore, because the electrical potential is higher in there. Okay, that will slow down the amount of calcium that's coming in, but remember there is this 15,000-fold gradient, so you have to think about which is going to be stronger here, and the desire to go in because of the concentration gradient beats the desire to go out because of the electrical gradient. And you know, this isn't going to become an extremely positive electrical potential difference here. At its very maximum, it's going to get to around plus 15 millivolts, and that's not that strong, not strong enough to oppose a 15,000-fold gradient. Okay, right, so once we've got up to about plus 15 millivolts, the voltage-gated calcium channels here are going to close, and that is not because they feel the voltage across the cell membrane having arrived at this positive value and say we're going to close. It's because they close after a certain amount of time after having opened. So they open very quickly once the electrical potential difference across the cell membrane gets beyond the threshold potential here, but they close very quickly. They're only open for a short period, so they're now closing. Okay, so that's stopping the calcium flow into the cell. And by the way, I hope I made it apparent that the HCN channels will have long ago closed because they like the electrical potential difference across the cell membrane to be hyperpolarized in order for them to open, and of course it's not hyperpolarized anymore. Okay, these ones close because even though it's still depolarized, and that's the cue for them to open, they don't stay open that long. Once it hits depolarization, they open transiently and then they close, and in order to get them to open again, what you have to do is take the electrical potential difference across the cell membrane back down to below negative 40 millivolts. Okay, you have to restore the electrical potential difference to what it was, and then if you then go above plus 40 millivolts, then they'll open again. Okay, but until you've taken it back down, they won't open again, so they're now shut. Okay, now what's going to happen, this is the depolarization phase of the action potential, the rapid upstroke as it's called, of the electrical signal. Now what we're going to have is the downstroke, and I've written that in a really inconvenient place because now I'm going to have to draw the downstroke over that, but never mind. And the downstroke is going to be brought about by another type of ion channel here, which is this time going to be permeable to potassium. So these are going to be voltage-gated potassium channels. And by the way, what I'm writing here, VGCC, this means voltage-gated calcium channel, this means voltage-gated potassium channel. Okay, so here what we're going to have is our voltage-gated potassium channels here in yellow. Okay, and again, these are usually closed, but when the electrical potential difference across the cell membrane gets to negative 40 millivolts, they open. Now, you might say, well, why didn't they open back here when the voltage-gated calcium channels opened, the T-type voltage-gated calcium channels? The reason they didn't open then is because they open extremely slowly. These voltage-gated calcium channels, these T-type voltage-gated calcium channels, they open extremely rapidly. They're very, very good at opening the instant the electrical potential difference across the cell membrane gets up to negative 40 millivolts. The voltage-gated sodium channels voltage-gated potassium channels are much slower about opening. Okay, so they, even though they were activated to open back here, only actually get around to opening after the T-type voltage-gated calcium channels have closed. So they're now opening, and what's going to happen is they're going to be permeable to potassium. So which direction is potassium going to move? Well, we know that the concentration gradient of potassium favours the movement of potassium out of the cell. Remember, it's about 40 times larger inside the cell than outside the cell. Okay, so the concentration gradient says go out, and also at the moment the electrical potential inside the cell is actually higher than the electrical potential extracellularly, so that will be an additional drive for the potassium ions to actually go from the intracellular compartment to the extracellular compartment. Now, moving positive charge out of the cell, that will do the exact opposite of moving positive charge into the cell, so it will lower the electrical potential intracellularly and raise the electrical potential extracellularly, taking the electrical potential difference across the cell membrane back to more negative levels, and the word for that is, of course, repolarization. Okay, so now what's going to happen is repolarization. So the electrical potential difference across the cell membrane will now start plummeting down, and even once we get to these more negative levels, once the electrical potential intracellularly is now back to being lower than the electrical potential intracellularly, of course that will mean that the flow of potassium out will slow, because now the potassium ions will want to be inside the cell because it's got the lower electrical potential and they're positively charged. But remember, the concentration gradient is still 40-fold going outwards. Okay, so that wins still. Okay, you'd have to get the electrical potential difference across the cell membrane down to something like negative 80 millivolts before that will be strong enough to actually stop the movement of potassium out because of the concentration gradient. So yes, it will slow the movement of potassium out, going to more negative electrical potential differences, but it won't stop it. So you'll get this nice repolarization here, and you'll get back down to negative 65 millivolts. And then again, what will happen is the voltage-gated potassium channels will close, okay, because we're now back below negative 40 millivolts here. And then everything's ready to go again. The HCN channels can now open, like so. So you'll get this phase coming again when the HCN channels have opened. When you get up to negative 40 millivolts, that will open the T-type voltage-gated calcium channels. Okay, you'll have the upstroke, which I'll try and draw here. And then they will close once we've got up to plus 50 millivolts, and the voltage-gated potassium channels will open again, and then you'll have another one here. Okay, another repolarization phase here. And that will be generated, this oscillation in the electrical potential difference across the cell membrane will be generated every 0.8 seconds, so, or thereabouts. So this period here in time is 0.8 seconds. Okay, so that then is how these sinoatrial node cells are generating this electrical signal, which is this change in the electrical potential difference across the cell membrane every 0.8 seconds. We'll have a break here, and in the next video what we'll talk about is how this electrical signal is going to be propagated to other cardiomyocytes, okay, non-sinoatrial node cardiomyocytes, and we'll talk then about the action potential, the electrical signal, the form of the electrical signal in those cells, because it is slightly different, it looks different, the graph of it looks different, and there are different ion channels involved.